Welcome everyone. It's a pleasure to have you here on my channel for the first video. This is Praneeth Lakshman speaking. He is an A-level student who's just finished his exam. So I'm just trying to dabble in higher level maths and physics and take you along for the journey. So I hope that you find these videos useful. I hope that you can learn something from them. And I also hope that you can correct me where I've inevitably make a mistake, and we can do this learning thing together. I mean, science is difficult, but science is so nourishing, so passion inducing that I just can't wait to share with you all the things I learn, and I hope you feel the same. I just want to create a community here where we can discuss higher level maths and science topics and we can improve each other's understanding. So with that 1 minute pitch out of the way, let's get on to the focus of today's video, which is the Black-Scholes PDE derivation. Now, there are many PDEs I could have chosen. I could have chosen the heat equation, the wave equation. This is definitely the top three is the third one, but I thought that this is a very good introduction. It's a very gentle introduction, and using this, we can start to link concepts in the other two PDEs, which hopefully you'll join me in the journey of doing. But first, we must start somewhere, and I thought this is a good recap on a lot of things that is new maths for people like me who've just finished A levels, but still approachable and still doable. So, let's go on to one of the most famous PDEs, as Veritasium calls it, the $1 trillion equation. Let's derive it step by step. So, the first thing we need to understand is the Wiener process or Brownian motion. Now, the name is interchangeable, but it was discovered near the end of the 1800s, and it was a way for randomness or random walks to be mathematically modeled. What does a random walk entail? What are the properties of such? Those are what things I've written down. So, W is just the path. Wt is the path position of some particle that is doing a random walk at time t. Now, the first thing, these are not ordered anything specific. The first thing we can talk about is that Wt has independent increments. So the increase in Wt, the way that where it goes, is independent of where it was before. Therefore, it is not a function that has an input as its last position. Number two is that every random walk starts at the origin. Number three is that the difference in position between two times the delta t is equal to some quantity u is actually equal to k, where k is normally distributed as with a mean of 0 and a variance of that u. It's an interesting property. It's probably the most important one we're going to use today. And number four is that Wt is continuous in t, but it is nowhere differentiable. And here I've got a plot for you. And in this plot, it is a bit bad here, but excuse me, but it is a very jagged plot and something you might be familiar with if you've looked at random walks in the past. It is something that's very jagged. Um, it's very jumpy, but it's very continuous. I mean, very continuous. It's just continuous. If I was to zoom in infinitesimal to an infinitesimal point on that graph, I would still see a line, and that's very important. Now we can move on to the the calculus of it. I mean, I've just said it's nowhere differentiable, and I'm talking about calculus, but you'll see that there is still some meaning to calculus in such a world where these paths are completely random and not an explicit function firsthand. So we want to define dWt almost as analogous to dx in normal calculus. And this is a very standard definition of dWt. It's just w at t plus delta t at a later time minus its initial time, and the limit as delta t goes to 0 is your dWt. And now we just want to do a recap of normal calculus. In normal calculus, dt goes to 0, but dt is very important to us. But dt squared goes to 0 even faster, so we can ignore terms with dt squared. That is something, it's a very important part of calculus actually, and we'll see the effects of that later. dWt similarly goes to 0 as delta t goes to 0, because this goes to 0 is just wt minus wt, which is 0. But importantly, dwt squared goes to dt. Why? Well, we now have to use the third rule that we discussed of Brownian motion. This wt plus u minus wt equals k. K is normally distributed and so forth. Here, if we were to plug in this into that, we would get just k, because this equals to k. But k is now distributed by dt. The delta t and the dt, I'm using them interchangeably. You shouldn't really. Dt is probably the better one to use, as it's going to 0. So dwt is it's almost equal to the square root of dt times k of n, where k of n is the standard distribution. It's like a random variable from the standard distribution, standard normal distribution. How can you do that? Well, I'd advise you to look at some revision of how to mathematically use random variables, but you can pull out the standard deviation out, and that's what this is, the square root of dt. And now if I was to square both sides, you get dwt squared is approximately dt. So actually, dwt squared goes to dt, not 0. So when we're doing calculus with dwt, we have to be very careful. So now we can move on to Ito calculus, named after the person who discovered this whole branch of algebra. Very smart man. We first start with the Taylor series. We're going to look at the multivariable version of the Taylor series. So here it is, recapped, and I've put the first order in green and the second order in blue. And well, I'm going to subtract f of x of t on both sides, so we get this delta f, and that's equal to f of x, and f of x and this are just different notation for the same thing. In such a place, if we ignore the second order terms for a second, if we forget that they exist and only look at the first order terms and change all the deltas into d's and so forth, you get df is equal to f of x dx plus f of t dt. And if you've already seen, if you've read ahead, you'll know that that's actually the multivariable product rule. And that's a very interesting link, and it's not a coincidence. And I want you to think about why that's not a coincidence. The multivariable product rule is just the Taylor expansion minus f of x of t for first order, and we can ignore all higher orders because of the fact that delta x squared, delta x is going to, as it goes to dx, goes to 0, dx dt, it goes to 0, and dt squared goes to 0 very quickly. So these go to 0 much quicker than the dx and dt counterparts. So having said that, we then look at a stochastic function. We look at a random function, x of t, where x of t is a stochastic function of t itself. In such a place, x of t needs to be treated more so as dwt, right? X of t is something that we will see later how it depends on dwt. In such a place, we still rewrite our Taylor expansion. We start off with that, but here we get this df. This is all the red stuff is things we know, and then the orange bit is where we have to look very carefully. Dx dt, dx times dt, we know dx goes to 0, dt goes to 0, so that goes to 0. Dt squared, we said, goes to 0. But dx squared, can you see how here we said that the random variable doesn't actually disappear? It becomes dt, or some multiple, depending on how x depends on wt. So likewise here, we cannot ignore this dx squared term. We have to keep it. And I've said it's almost dt, it's just some scaled version of dt. So if you make all the things 0, well, you get df is equal to f of x dx plus f of t dt. And there's an important correction term almost of half f of x, fxx of dx squared. This last bit is called quadratic variation. So if you want to look at that in the literature, you can, but that is the quadratic variation. And that's what makes all of this calculus different to what we're used to, this Ito calculus. And the last statement is so important, it's called Ito's lemma. Lemmas are statements that from which everything else builds upon. And so here, this is the most important result after the, before the Black-Scholes equation that we can use. Now that's a lot to take in, a lot of stuff, and I even haven't defined x of t yet. So we're going to do that next, okay? I told you x of t is a stochastic function. So in practice, when we're using Ito's lemma, we'll see what that means. So stochastic functions can be modeled. I mean, they're modeled as Brownian motion, but Brownian motion comes in many different forms. The most simple of which we will talk about is arithmetic Brownian motion, which is just mu dt plus sigma d dwt. Here we have our dt, our normal calculus operator mu dt is called the drift term. So even though x of t is a random variable, it has its tendency to move somewhere, and that tendency is what we call the drift term. And here we have the random term because it's dependent on dwt, which we've just talked about how it's a random process. Notice how I didn't define x of t. You don't really define x of t. You want to define how it behaves, and that's very popular in modeling. So it makes more sense to define the behavior of x of t rather than x of t itself, because that's often the unknown that you want to find. So here we want to, for an example, let's take f of t, x of t, and a very simple function is equal to x squared, where x and x of t are interchangeable. Now, we want to sort of find how this function behaves, so we can use Ito's lemma. So Ito's lemma, if you've just forgotten, is this. I'm going to keep that there on top. So df is equal to f of x dx plus f of t dt plus a half f of x dx squared. Now we can substitute what we know of that dx into this equation. So we get f of x mu dt plus f of x sigma dwt plus f of t dt plus a half fx x, and then we want to square all of this, so d plus sigma dwt all squared, collect dt terms, f of x mu plus f of t dt plus f of x sigma dwt plus a half fxx, and again we need to now pay attention here because mu squared dt squared plus sigma squared dwt squared plus 2 sigma mu dt dwt. Well, we know that dt squared goes to 0. We know that this goes to 0 because there's a dt and dwt, both of which go to 0, but dwt does not go to 0. In fact, we can now go all the way up here, and we know that dwt squared actually goes to dt. So now I'm gonna change color to show that we are in uncharted territory. So we get f of x mu plus f of t dt plus f of x sigma dwt plus a half fxx. We're just going to keep this because everything else goes to 0. Dwt squared is dt. And now collect again. F of x mu plus f of t plus a half fxx sigma squared dt plus f of x sigma dwt. Notice how if we didn't consider this quadratic variation, we would have just left it at this. This term would not have been feasible to get, and there would not have been a kind of randomness. So this is a very important result. I'll leave it to you to find what f of x equals. I've given you the function, what f x equals, and what f t equals. They're all very simple to find. You can plug it back in and have fun then. And here it just shows you how f changes, right? So if you have all of these parameters, mu and sigma, then you can use code, which you'll see later in the series how to do that, and we can model this. So we'll get back to this later, and I'll show you the solution in a later video. So now we're going to go to the Black-Scholes equation. We're going to do it in 5 steps. So number 1 is the 0th step. I'm cheating, I'm sorry. It's going to be define. So we're going to define stock price, S of t, and if you don't want to think about finance, that's fine. just think of stock price as x of t from before, and it's a stochastic process. So we're going to say first S of t is stock price at time t, and stochastic process, so it's equal to mu dt plus sigma dE wt. However, it's geometric, it's not arithmetic, which means it scales by its current position. Not the position before it, which would violate the increment thing I talked about, the first law of the Wiener process, but its current position, which is completely fine. So we have S of t and S of t here. And so that is your stochastic process. And we assume that V of t, S of t, is the value of an option. And I'll talk about options and all later, but just think of this as a function for now. This is all just a function at time t when stock price is S of t. Because S of t, the reason why I say S of t is because S is also dependent on t. It's a function of t. So now we're ready for the first step, which is always going to be, in this situation, apply Ito's lemma. And if you're wondering, why have you not defined an option yet? We'll get to that when it makes more sense. Here we can just do maths and kind of bury our head in it. Apply Ito's lemma. Well, Ito's lemma, if I was to just very quickly write it here, is f of x dx plus f of t dt plus a half fxx dx squared. That's Ito's lemma, and we're just going to apply it here. F is v, x is s, so dv is equal to f of s ds plus f of t dt plus a half fss of ds squared. And like before, we substitute ds's and so forth in. So f of s, just f of s, and then we have f. These not should be f. That's just habit. It's v of s, v of t, v of sss. So you have v of s, and ds is all of this. So s, and I'm going to say s is just mu s of t, of course. So s mu. I'm going to put mu s dt plus sigma s dwt plus vt dt plus a half vs s. And we know from the squaring thing that only this thing survives anyways. So we're going to have s squared, sigma squared dt. This is just from our example earlier. Just say it was a bit of algebra of squaring and unsquaring and so forth. So we can collect dt terms now. So we have vs mu s plus vt plus a half vss s squared sigma squared all times dt plus vs mu sigma s dwt. Cool. And this is our drift once again, where it wants to go, and then this is the randomness in the process of our option, or just a function if you don't want to think about it. So we now go to the second step, which is now add finance terminology. So what an option is nothing but a contract. So we're going to look at options first. So option, stock price, I assume you know what a stock price is. An option is an interesting, it's like a contract, right? And you have person A, you have person B. In an option, what it says is, let's say today's date is the 7th of July. That is today. Let's say on the 10th of July, so in 3 days' time, so 3 days time, so an option says, so this is the seller, A sells, B buys, A sells the option, right? So he like sells the option now, and an option is just a contract saying you can you have the right to buy this stock at a later time. So the seller goes to A goes to B and says, look, today's the 7th of July. On the 10th of July, you can buy the stock from me at the price we agree now. So that's the important bit, at current price. So let's say he holds £5 in stock. He says, look, I will give it to you for today. I will give it to you for £5. Today's price. This can change. This could be some other price, but for simplicity's sake, we're going to just assume it's today's price. I'm going to sell it to you for £5 in 3 days' time for this agreed price. And B goes, okay, that's fine. Now, A wants the stock to, and I'm going to highlight this, to drop. Why is that? Well, because if in the later day, let's say at the green time is the later day, he gives it for £5, but it's actually worth only £3, well, he's just made plus £2 profit, because he can just because he sold it for £5, he's now got £2 profit, £2 more than what the stock is actually worth. B, of course, wants the stock to increase. Let me write that in a different color. Increase. So he wants it. So when he looks at this transaction, he wants it to increase. So he wants it to go for 7, because now if he sells that on the market for something else, he makes plus £2. So we call these in finance. There is 2 different terminologies for this, right? So this A seller, we say A is shorting the stock, i.e. A wants the stock to drop, and B wants the stock to go up. We call them, he's in the long position, so long. So you have short and long, it's just the opposite of each other. So long is buying low and selling high, and shorting is selling high and buying low. So we now can construct a portfolio. A portfolio just means owning more than one thing here. Portfolio P. Now the idea is that this, as we've seen before, this stock DV and DST has this random bit which we don't want. We don't want this randomness because that's risk, in other words. So to minimize our risk, we can do something very clever here. We can say, well, we have this portfolio, and we're going to buy this option V, this contract here, and then we're going to also like short the underlying stock. So here we're in a long position because we're B here. If you think about it, we're person B here, and then here will be, if we buy the stock, short the stock, sorry, we're actually person A. So we're being both B and A on the same stock. And now the important thing is we own a fixed number of that stock, the underlying stock. So V is also dependent on S, but we're basically being both A and B here. And the idea is that by having enough of exposure on both sides, we can actually get rid of risk. That is the idea of Black-Scholes, right? We want to have risk-free portfolio. So, and that's a fixed number of stocks, S. So, we want to remove the risk terms. That's our third step. So, remove risk. So, we have P equals V minus delta S. If we take the differential, it's dP is equal to dV minus delta ds. Now substitute everything we know about these things. Here I'm going to jump a few steps because collecting and stuff, it's a little bit boring, but you can go and take dv from earlier and ds from earlier, and I'm just going to get to you in the last line, which is vt plus vs mu st, sorry, mu s, I'm just going to make it mu s plus half vss sigma squared s squared minus delta mu s, which this cancels here, dt, sorry, not yet, it doesn't cancel, that's my bad, whoops, spoiler, dt plus vs sigma, I'm going to make this in a new line, plus v s sigma s minus delta sigma s dwt. And because we want to remove risk, i.e. want to remove the randomness, we're going to have to set this equal to 0. And that's where this whole trick comes in. We go v s delta s, sigma s is equal to delta sigma s. Here, these two cancel, so we have vs equal to delta. So we know that in other words actually, it's the dv ds is equal to delta. So one, we know that this is actually a constant, which is something interesting, and we can use that later. But two, we have now this sort of relationship that we can plug in to here. We get, so here you get dp is equal to vs mu s, and delta is now vs mu s, so these cancel now, so you just have vt plus a half vss sigma s squared dt. Look at that, so we've reduced the risk completely, we've removed the risk by just setting them equal to 0, setting the dwt term equal to 0, and we're now left with this expression. Now, we know we have a risk-free portfolio, so a risk-free portfolio. What does that mean? So, well, P, the change in P should be equal to the price of P are the same. And DT, no DWT because it's risk-free. And ideally, we want it to grow at a risk-free rate. We call that R. And R is like 1.2, 1.3, something like that. That's like 30% increase and so forth. And of the current price. So we just left with that. Now we can set these two to be equal to each other actually. And you get RP is equal to VT plus half VSS sigma squared S squared. Or P we know from before is V minus VS. Or I can say delta, but it's VS now we know. S equals VT plus half VSS sigma S squared. And we then go, well, I'm going to stop here and I'm going to say final step, rearrange. Isn't that interesting? So we'll rearrange. We get RV minus RVSS equals VT plus a half VSS sigma squared S squared. And I'm going to use all this space here. We're going to say VT plus a half VSS sigma squared S minus RV plus RVSS equals 0. And would you know it? That is the Black-Scholes PDE. So we've done it. With very minimal understanding of the Wiener process and so forth, we built it up slowly. We understood how how calculus is different when we're looking at random processes. We then use that in an example problem to consolidate our understanding, and then we applied it to finance. We defined the stock price, we defined an option, we then applied Ito's lemma that we derived earlier. We then added the finance terminology and then constructed a portfolio in which we were both the seller and the buyer of the stock. We were playing both sides, right? And that's always how you get ahead. You play both sides. So by playing both sides, we remove the risk by setting the random part of the differential of p equal to 0. And when we did that, we found this relation that the partial derivative of v with respect to s is equal to delta, and therefore we got the simplified equation for dp. And then we knew that what a risk-free portfolio should look like, and then we rearranged and we got the Black-Scholes PDE at the end. In another video, we'll look at how we can try and solve that and how it links to the heat equation, which will be an interesting video. But until then, hopefully this was informative enough. Hopefully my explanations were clear. If you have any questions, please leave them down in the comments. And I hope to see you here soon to see more maths and science topics. Lovely having you here for my first video, and first of many, hopefully. Goodbye.